Hello out there, thank you for watching my video today on graphing rational functions with oblique asymptotes. To start here, we have an opener, which is a polynomial. I'd like you to solve when that would be 0. Remember to create a PQ list, and you can test those rational zeros using synthetic division. Once you've found enough zeros, you can plot a graph, and then use your graph to answer the inequality question third. Pause the video at this point and come back and check when complete. All right, you should have came up with something along these lines here. You got 4 answers for A. All of them are linear factors, so you'll pass through the graph, the axis at each one. You can use your graph to see that the function is positive on 3 different intervals here, here, and here. Okay, so let's take a look at what we're going to learn today. We're going to talk about rational functions and oblique asymptotes. But let's go back and talk about horizontal asymptotes as well. Remember, this is a rational function, and we talk about m being the degree of the denominator and n being the degree of the, m being the degree of the numerator, and n being the degree of the denominator. And if n is bigger than m, we have a horizontal asymptote at y equals 0. Every time, no matter what. If n and m are equal, we do leading coefficient over leading coefficient. And now the new one for today, if n is 1 less than m. So if it's 3 over 2 or 7 over 6, something along those lines, we'll have an oblique asymptote at some linear equation, which is what we'll have to find. Now, if n is 2 or more less than m, then there's neither a horizontal or an oblique asymptote. So let's take a look at what we should have already learned, finding horizontal asymptotes quickly of these functions. The first one, the degrees match, so it's leading coefficient over leading coefficient, so it's y equals 1 over 1 or y equals 1. Second one, again, degrees match. So it's leading coefficient over leading coefficient. It's just y equals 2. And a third one, it's bottom heavy, we would say. The denominator's degree is higher. So that's just automatically y equals 0. So that should be pretty quick at this point. However, if it's oblique, it's going to take us some time to work through this. So I have a couple examples here. We need to use long division to find the oblique asymptote, which also can be called the slant asymptote sometimes. And then once we find that, we're going to use that and all of our other information that we know to graph. So first of all, how do I know this has an oblique asymptote? Degree of 3, degree of 2, the numerator is 1 higher. That tells me it's an oblique asymptote. So we're going to set up our long division. Make sure that when we set this up, we use our fillers here for the missing terms. So 3x cubed over x squared is 3x. Subtract, we get 3x squared plus 21x plus 2. 3x squared over x squared is 3, so plus 3. And you can actually stop there. You don't need to go through the next step of finding the remainder. Our oblique asymptote is simply 3x plus 3. Okay, so if we were to graph that, looks something like that probably. Now remember, this is an asymptote, so it should be dashed. Okay, so the rest of our process that we've talked about here, finding intercept, so we know what our y-intercept would be at 0, -2/7. So we'll plot that, 0, -2/7. So it'll be somewhere around there. X-intercepts, if we set this equal to 0, let's see, we get 3x cubed equals -2. So x cubed equals -2/3. So x would equal the cube root of negative 2/3. I'm not going to lie to you, I don't know what that is, but I know it's a pretty small number here of negative. It's a pretty small negative number here, so probably something along the lines of right about there. Okay. And then we can find our vertical asymptotes by trying to factor the denominator, which isn't going to factor, but if we use quadratic formula, we'll have 1 plus or minus the square root of 1 plus 28 over 2. So it's 1 plus or minus root 29 over 2. Root 29 is a little bit bigger than 5. So 1 plus 5 over 2 would be a little bit bigger than 3. So x equals 3. And 1 minus 5 is negative 4 over 2 is negative 2. So now that we have all of our asymptotes there, we can start picking some points. So if we pick a point like negative 3 or negative 4, and we put that back into our original equation, you can use a calculator to help with this. If we put negative 3 into there, we would get approximately negative 16. Again, you can use a calculator to help you with this. So it's going to look something like this. In the middle, we're going to follow this asymptote up here and this asymptote down here. And then on the right side, if we pick a number like, I don't know, 4 or 5 or something along those lines, so 3 times, let's go 4 cubed plus 2, divided by 16 minus 4 minus 7. And you get a pretty big answer of like close to 40. So our graph's going to look like a parabola, kind of, up here, following both of these asymptotes to infinity. So let me make my graph a little bit better here. This is going to keep going this way. This is going to keep going this way. So we have a graph that looks like that. All right, so the important part about this problem here is that we were able to find the oblique asymptote of 3x plus 3. The graphing part will be a little bit easier when we have a little practice with it. But really, again, we're talking about the same thing we talked about before, making sure our asymptotes, our end behavior, and our x-intercepts are correct. Otherwise, the rest of the graph can be a little off. Okay, let's take a look at B. And let's try to find the oblique asymptote for this one. How do I know it's oblique? Again, this is the second power, this is the first power, so I know this is oblique. So I set up my long division. And if I divide, we get 5x. So 5x squared plus 10x. That'd be negative 13x plus 1. And that'd be negative 13. And again, we don't actually need to keep going at this point. We have negative 5x minus 13. That is our answer. That is where we can stop. Okay, now we can figure out what else we need to figure out and go from there. All right, so let's start with our vertical asymptote, which would be at negative 2. So there's our vertical asymptote at negative 2. Okay. I probably should make that a little bit longer since I know what happened in the last problem there. Okay, and then my horizontal asymptote doesn't exist, but I have an oblique asymptote, 5x minus 3. Let's draw that in a little bit later here. Let's find some other information might be helpful here. X-intercepts and y-intercepts. So the y-intercept would be 1/2, so 0, 1/2. Okay. Let's see if there's any x-intercepts. If we set our numerator equal to 0, you can use completing the square or quadratic formula for this. So that would be 3 plus or minus 9 minus 4 times a times c. So that'd be 4 times 5 times c, 5 times 1. So that'd be negative 20. And you can figure out from there. These are going to be imaginary. So there's no x-intercepts for this problem. Okay, back to our graph. if we put, let's say this is negative 13 right here, we'd have our graph look something like this. Our asymptote would look something like this. I'm going to put that as dashed line since it's an asymptote. And it looks like I need to extend my vertical asymptote a little bit further here as well. So I know what one part of my graph is going to look like. It's going to follow these asymptotes forever. And the other part, if we pick like maybe -3 or -4 or -5 or -6, we're going to get a point somewhere over here so we can follow the asymptotes like that. So that's what our graphs are going to be like. Okay, so the oblique asymptote is very similar to the horizontal asymptote in which the graph can intersect it once, which it does in the first problem here, but not in the second problem. So on the next slide, I'd like you to try this on your own, just finding the oblique asymptote. You don't have to graph anything. Just practice a long division and find the oblique asymptote for each, and then you can check your answers when done by unpausing the video and seeing what we got. So here are the 4 oblique asymptotes for this problem. One more time, let's pause the video. There's one problem left, that's a graphing problem. So this one will have an oblique in it, but it should be easier to do because there's a lot of things that factor nicely here. So pause this video, try this one, plot the best you can, and then come back and check your graph when done. And hopefully you came up with something like that. Now notice one thing here about the end behavior. As x goes left, y is going to go down forever. Slowly, but it's going to happen. And as x goes right, y is going to go up forever. Again, slowly, but it's going to happen. So the end behavior for obliques is again going to be positive or negative infinity usually, just like our polynomials were. That'll do it for our lessons on graphing rational functions. I hopefully you have learned a lot here, and if you have any questions, you can always drop in the comments or ask me in class. Thanks again, and we'll see you again soon.